Hi everyone!
Hello, everyone.
First of all, thank you so much. We're really honored to get the Maurice Wilkes Award.
It's especially humbling because we know there's so many people that deserve this award, and also there's so many people that contribute to the work alike to this award. So thank you. So we thought we'd start telling a little bit about how we got to this. We were interested in DNA computing, and we had a fantastic collaboration with Georg Sillig, who's a good friend of ours and a professor at UW, who did molecular computing with DNA, and that was our first result in this space. It was an ISCA paper on spatially localized components in DNA computing. And then that same year, we went to Cambridge for a sabbatical. And of course, Cambridge, there's DNA everywhere. And that happens, we happen to be at the right place. And while there, we saw a talk by Nick Goldman, who was, a leader in this revival of DNA data storage, whose original idea actually dates to the early 60s. And we saw a talk by his work on DNA data storage. And then we got really lucky because they got us so excited. We realized that DNA data storage was exactly at the intersection of our interests. Karin's work on emerging memory technologies, my interest in approximate computing and machine learning, and then biology, a common interest of ours. So at the dead center of this intersection was DNA data storage. So we got back super excited.
The more we looked into this area, the more excited we got. And our approach was very much from a systems perspective. So we started by comparing DNA with other types of media that would serve the same purpose. And we saw that the density potential for DNA was super high. Also, durability was something that seemed very interesting. We know that DNA can last for a long time if under the right conditions. And now that we know how to read DNA, we'll always be able to read it. And so there's also, it doesn't go obsolete. In addition to that, a lot of questions popped up. So here are a few questions as examples. Random access issues, hardware-software interface issues, how to automate the whole system end-to-end led us to the research that we're doing right now. And an even more exciting question was, can you do computation with the data directly with molecules? At that time, Doug Carmine had just joined Microsoft. Doug's a really forward-looking architect, and he really helped us think about the project at the large scale. He helped us get the project off the ground and made many great contributions to the project as well. This was really fun and productive collaboration with Doug. Speaking of forward-looking architectures, here's how we think about this opportunity. So there are things that electronics can do well and things that molecules can do well, and we're really thinking about this end-to-end in a hybrid molecular electronic system. And so it goes all the way from encoding, which is done in the electronic domain, into placing the information in the molecular domain, storing it and computing over it, and then recovering it, placing it back, bringing it back to the electronic domain, and then doing additional computation over it so we can recover the data.
So we spent quite a bit of effort also prototyping systems because we wanted to get a taste of what it takes to actually build a system with electronic components and molecular components. So the molecular components involve controlling fluidics, controlling the movement of fluids to carry out the chemical reactions, as well as ways of programming it to do what you want it to do, and then interfacing it with the DNA writing part, which is synthesis that we're showing here on the left, and also sequencing, which is the process of decoding and reading the DNA back. So putting the systems together was eye-opening in showing us what would it take to actually build this for real. We thought we would highlight a few research results that we got along the way. It spans from molecular biology to systems and all the way to ways of mapping algorithms in molecular form. So on the molecular side, we explored ways of pushing the limits of information stored in DNA, understanding its properties as we scale up, thinking from a systems perspective, including hardware-software interface, which was the topic of our ASPOS paper, then demonstrations of the fluidics part and automation. And on the algorithms and computation side, we as we were doing the encoder and decoder, we realized that we needed to develop new ways of clustering large amounts of data to do the decoding. That led to an algorithms contribution. And then more recently, we looked at how to map things like a similarity search directly in molecular form, because that not only takes advantage of the density of DNA, but also the high bandwidth molecular interaction that can favor computations like similarity search.
And in doing this work, we did some, let's say, unusual things. One of them was to build a lab, the Molecular Information Systems Lab, and we're very grateful to the School of Computer Science and Engineering at UW who gave us a home and let us build the lab.
One of the things that makes this lab special is that it sits in a computer science building, so it's already leading to a lot of interesting collaborations with the machine learning group, with folks doing security, and we're very proud of that.
All right, and we also had some fun. So a little bit of art here. We encoded a high definition video for OKGo and had them visit the lab and also display a little gift that we gave them during one of their performances.
Speaking of art, we had a recent collaboration with Kate Thompson, who's an artist that spent time with us, and she did really interesting work on encoding images that we had put into DNA and mixing into paint and doing a mosaic of Rosalind Franklin's portrait. And we thought this was an interesting self-referential and deep way to pay honor to Rosalind Franklin, which is instrumental in the discovery of DNA. Popping back up to computer architecture, I wanted to emphasize that there are a lot of opportunities in the intersection of areas. We've been exploring molecular electronic computer systems and the interface between them, and we think there's several opportunities like that in the intersection of fields and the intersection of trends, and we encourage you to think about these intersections as well.
Finally, we didn't do this work by ourselves. We collaborated with a fantastic group of very diverse researchers who have been doing a wonderful job at the project. So thanks, everyone. And thank you so much for this honor.
And of course, I'd like to thank our advisor, Joseph Torellas, for guiding us at the beginning of our research careers, and mentors like Doug Carmine, Doug Berger, Hank Levy, Susan Eggers, Ed Lazowska, and many others who shaped up our careers. And finally, we'd like to thank the general support of our research by several institutions like Microsoft, University of Washington, DARPA, and the National Science Foundation. Have fun at ISCA!